Good morning, everyone. Welcome to Organic Chemistry 2, review session part 2. And we've had some good requests. And one of them was, can you go over how we put groups on benzene, carbon groups? And we're going to do that right here. If I can figure out why my things are all tangled up. Here we are. Okay, sorry about that. And here we go. We're starting with benzene, and we have to put a methyl group on benzene. How is that done? Well, remember, all the reactions that put a carbon group on benzene require the same catalyst, and that's aluminum chloride. So everything here is going to have aluminum chloride. And a methyl group on benzene, you need a methyl with a halogen on it. And I've got all the answers here on the next page. If you want to put a methyl on benzene, you methyl chloride and aluminum chloride with a catalyst, as the catalyst, sorry. Putting a carbonyl group on benzene, and just a reminder, if we have R equals H, we've put an aldehyde on benzene. Yes, R can equal H, unless I say otherwise. All right. And R equals C would put a ketone on benzene. And that's done with an aluminum chloride catalyst as well, except we have to use an acid halide. And all of these are in chapter 22. And I'll do that one, and then I'll use that information to figure out how to put a primary alkyl group on benzene, because we don't know how to do that directly. And we are told that on our retrosynthetic analysis, both today and the one we practice, and on Wednesday on the one you're doing during your test, you're going to have a primary alkyl group on your target molecule. First, you have to put an aldehyde or a ketone on the benzene. I suspect you won't be putting an aldehyde on the benzene. Here's why. Because to follow this protocol, you're going to reduce the aldehyde to a methyl in the next step, and we already know how to do that in one step. Put a methyl group on benzene. So let's just look at the ketone options over here. R would be a carbon group. Aluminum chloride would put a ketone on. Here's what they would look like. And then you reduce the carbon attached to the benzene, which is a carbonyl, under the Clemmensen reduction conditions. And the Clemmensen reduction conditions are useful for molecules that are sensitive to bases. So this has an acid in it. So if your molecule is sensitive to bases, then don't do this one, do the Clemmensen. If your molecule is sensitive to acids, then do the bottom one instead. Sensitive to means reacts with. And this is called the Wolff-Kishner. Take you back to the start of the semester. And the main reason we learned both the Wolff-Kishner and Clemmensen was so that we could put primary R groups on benzene. We didn't know it at the time. We were told that it was coming, and it has come. So there you go. You're going to put a primary group on by putting a ketone, then reducing it. Secondary groups can be put directly because carbocations are possible from them. The reason primary groups could not be put on directly is primary carbocations are not possible. The methyl reaction doesn't make a cation. It makes a methyl with the other chlorine on the other side, and methyl has a leaving group. Okay, secondary alkyl groups. Secondary carbon with a halogen, aluminum chloride generates carbocation, and you get your secondary group. Tertiaries will go faster because the cation is more stable. It will form faster, and we get a tertiary group on our benzene. I'd like to remind you, both of these reactions generate carbocations. So other reactions in the past that generated carbocations can be used instead of these protocols. So if you needed a carbocation from an alkene, you could do so using sulfuric acid or toluene sulfonic acid. Similarly, a tertiary alcohol can be made into a cation with sulfuric, toluene sulfonic, or even phosphoric acid. We saw that one last week. And that is a request for a little overview and then into some actual exam questions. We had a request for this one. Winter 19, Test 3, Part 4. We're on page 3. That's good. Let's see what happens here. We're putting a group. We can't put it on the para position to the O, which is where we want to put it, because there's already a group there, and it's going ortho. That makes sense. It's an ortho para director. Notice I didn't even talk about the cyano. I don't need to talk about the cyano because this is a more powerful directing group. It takes over. This one is almost identical to a review item we did Wednesday. We used acetone instead of this. We made bisphenol A. We protonate that. Activates the carbonyl towards an attack. For the interest of variety, I'll actually have the oxygen participate in the EAS here. If you want an example, oh, I can't use red though. If you want an example where I didn't use that lone pair, just look at Wednesday's review. This is optional to do the resonance part here. It does explain why it goes a lot faster with a lone pair on the atom attached to the benzene. There we go. I'm going to get this thing. We've lost our aromaticity. We've got a double bond to O. Benzyl group attached to the O. Didn't touch this. Didn't touch this. Didn't touch this. Got a new group attached right down here. There's an H that's old, and the new group is in green. We got ethyl on each side and alcohol here. Red first, blue second. See how we can get the ball going in the next one. We've got it re-aromatized with the conjugate base we generated in the first part. OPO3H2. Dihydrogen phosphate if you're looking for a name. First step definitely would be re-aromatization. This thing is itching to be aromatic again, and there it is. And later, I'm looking at this carbon with the two ethyls. There it is. It's got the OH, and there it is. Okay, well, apparently I'm in the box. I was thinking I could start the next mechanism right now, but seeing as we're going to the box anyway, let's do stuff from here. Nope, lone pair, not showing. We have to make that into a leaving group, same acid present. Remember, square bracket without a telephone pole means this is an intermediate. Just me trying to help you do the mechanism. And it's going to leave. I think we can get some stuff going on here. It'll leave, that'll generate a carbocation. Tertiary carbocation. And that will get attacked by another molecule. Notice there's an excess here. We're going to have to copy another version of that molecule down here. And what do we got? I'm going to go ortho on that one too. And we have a paracyano. We have a lone pair. Same story as before. Lone pair resonates. Ortho pi electrons attack. Can't use blue. That would mean an SN2 reaction. Just think about this. I'm going to finish it, and it's wrong. This is why showing me there's two different things going on is important. The arrows I put on the screen right now reflect an SN2 reaction on a tertiary carbon, and I don't like seeing that because that's not what's going to happen. I need you to clearly show a carbocation being generated. So the first blue arrow here is fine. That would indicate a carbocation being generated. And I need different colors for these arrows because then it's the last step where we attack the tertiary carbocation. And I hope you found that step breakdown illustrative. And we have a double bond here. May be able to circle a whole bunch of R stuff. A little awkward here, but it's okay. We can figure this out. There's an R. We'll put the R on at the appropriate time. Looking at the mechanism we started, we definitely have an H here. Didn't touch this pi bond. Didn't touch the cyanide. Didn't touch this pi bond. Got a cation here. We have a new group. New group. Carbon with two ethyls. Right? Attached to R. Yellow R. Yellow doesn't show up very well. I'll just put it in black. There we go. And we have to get from there to here. And what's going to get us there? We got to let re-aromatize. We need our same conjugate base. Dihydrogen phosphate anion grabs H. Sigma becomes pi. Resonate to neutralize the O. And you're home free. You've done your di substitution reaction. So you're definitely looking forward to something like this on your test. We did it on 2 review days. We do a similar reaction twice, starting with a ketone. I'm thinking about it right now. I might be making that question up right after this review session. All right, no mechanism. What's going on down here? Wow, a couple things happened, and it's only worth 1 point. My goodness, how can that ever be? Is that a typo? It's not. I have a set of chemicals that can reduce a cyano to an amine, CH2NH2, H2PT. And the same set of chemicals causes what's called hydrogenolysis. So you want to also review hydrogenolysis. So we got 2 things going on here. I'll put a big old star. 1, reduction of nitrile. And 2, hydrogenolysis. And that creates toluene. I want to remind you this is toluene. It's got an extra an extra H on the C. And the other H from the H2 ended up on the alcohol, didn't it? Okay. So there you have it. And we can probably look at at least introduction to the next part. I think I went forwards. Yeah, we had a request for this one and then another one on a different exam. Oops. Yeah, that was the one on the different exam. We can do the multiple choice one first. And the student was obviously perplexed about the guanidine because I don't know if we talked about it. And I gotta tell you right now, that's an omission on my part. Guanidine is an important biological base. And I'm supposed to know how to draw it. And it's found in a lot of things, like the structure of guanidine. I actually see it down here almost. Down here, as in right here. This little centerpiece is a carbon version of guanidine. If you make this an NH2 and make this into an NH and this into an NH2 and get rid of all the scaffolding, we call it out here, then you have guanidine. So how do I draw guanidine? Well, here it is. You learn to answer these questions. I don't think I'm putting that there lightly. H2N goes C double N with an H and an H2. And I'm going to tell you, I told you it's a very important biological base. And there's none of this in nature because of this. What? How can it be a biological base if there's none of this in nature? Here's why. Here's the answer to question 2, sorry. PKB is darn close to 0. What kind of a base is that? In biochemistry, that's the strongest you're ever going to get. Which means if there's anything around with a pKa that's even, say 7, it's going to take it off. 5, it's going to take it off. Anything above 0, it's going to take the H off. And what's it going to become? Great question, by the way. Where do you park the H? I want to just say you've got lone pairs on every nitrogen. And only one of these lone pairs is appropriate. And it kind of goes against something we learned earlier. We learned earlier that an sp2 cation is not as stable as an sp3 because it's got lone pair closer to the lone pair. It's got the plus charge, closer to the nucleus. If you put a plus up here and an H, it's sp2. You say that's not as good. But there's something much more important than that. It can resonate with both of the other nitrogens if you have a plus charge up here. If you put a plus charge here, resonance is over for this nitrogen. It's got 4 sigma bonds, not a resonator anymore. Don't put it there. Same story over here. Park it up here, and it can resonate with these lone pairs. It's got a pi bond that can become a lone pair. And you get 3 equal resonance forms. So guanidine, 100% of this in nature. All guanidine in nature looks like the one I'm about to draw. %100% of guanidine in nature looks like this. Conjugate acid, right? And it's not a very good acid, is it? It's a very stable acid. pKa is roughly 14. Where did I come up with that? So we always memorize pKa's, but in this case, I strongly suggest you memorize the pKb of its conjugate base because it's a nice, easy number. And then you figure out pKa because it's 14 minus pKb. And my attempts at doing an A are getting worse and worse. Here we go. It looks like an A. So it's our strongest base. It will be at the end. This is an extensively resonance stabilized base. That's all I'm going to say about it. You should be able to draw the resonance forms. Use lone pair here. resonate in, you get an NH2 there that looks like this old NH2. Same story down here, same resonance up to the top, or from the NH2 lone pair here, resonate back. Lots of good things going on. Parole, we learned, well, we're supposed to know what parole is too. And that was on a other cautionary list. Oh, what did I do there? I got to a test. Went to a different program, sorry. Boom. Parole looks like this. And it's an aromatic molecule because nitrogen has a lone pair. You park an H on there and it's no longer aromatic. So that's terrible. Big old eraser. I'm not going to redraw. It's fine. Parole is a terrible base. And then we're supposed to be able to compare a secondary amine, which we thought were the best bases until we learned about guanidine, to primary amines. Oops, we got to put an N in there. There we go. And the secondary is a little better because it becomes an ammonium ion that has double hydrogen bonding, double hyperconjugation. This becomes an ammonium ion with triple hydrogen bonding and only mono hyperconjugation, mono substituted. So 3's a little better than 1. New scratch on my screen. Great. Sorry. 4132. I hope that's one of the answers. There it is. DE. On the test, I'd probably just have you put these in order without choices anymore. Hunting down the choices is sometimes time consuming. And yeah, now that it's not really multiple choice, I can give you partial credit if one of these is out of position. Isn't that nice news? We had a request for part 3 over here of this one, and it's the guanidine one. So I think with that new information, we can actually answer this. We're going to draw the guanidine. So where are you going to park the H this time? Well, it's the same story as up here. You put it on the sp2 nitrogen so that it can resonate. I want to remind you there's another story with imidazole that's similar. Since we're on the subject and it's very related, imidazole looks like this. It's not on this question, but it could have been. And it's a cool molecule. It's got a pKb close to 7, which means its conjugate acids pKa is close to 7 as well. It means in biochemistry, you have, if there's an imidazole containing functionality in a molecule, half the time it's protonated, half the time it's deprotonated. And once again, this is the lone pair to use. The red lone pair, don't use this one. And even though it's an sp2, which you'd think is not as good, this one's being used for aromaticity. This one's not. You're saying, why not that one? Well, I'm telling you, nitrogen that's already pi bonding with carbon that way can't use pi electrons here too for anything else. So it stays in a hybrid up there. These become rehybridized to p so it can resonate with the other pi. So similar story, protonate the sp2 nitrogen here, protonate the sp2 nitrogen here, protonate the sp2 nitrogen down here. And we will faithfully do that right now. Plus charge. And another ring. Oh, we got a nitrogen in this corner. And a nitrogen here. Don't protonate that one. 1, 2, 3. And pKa roughly 14. Hey, show off that you memorized the pKb. Because you know the pKb here is 0. How do you know that? Because you were just taught it. I believe we talked about trifluoroacetic acid. And his pKa is darn close to 0. That's a nice little review item here. Where are the zeros? We got 2 new zeros. 0 pKb and 0 pKa. It's got a lot of inductive effect, doesn't it? So pKb here, 14 minus 0. All 14ths. And we like going from a low pKa to a high pKa. So we're circling the arrow going down. And pKeq. Oh, we didn't even have to calculate pKbs. Sorry, it's not here. It doesn't hurt to do it. pKeq is the acid on the reactant side, which was 0, minus the pKa on the product side, which is 14. KEQ big time to the bottom of the screen. So I guess you call this an alkyl guanidinium. How's that for a name? Because it came from a guanidine with carbons attached. So an alkyl guanidine. I didn't write that down. Sounds nice. Alkyl guanidine is now an alkyl guanidinium. Guanidinium. Okay. And I hope that satisfies that student's need for help on this one. We filled in the missing piece. We did the pKa's there and there. We did the pKeq and the KEQ and circled the arrow. Good. And that's a good spot for our first break, a rather longish first segment. I will let you know what we're starting with in the next one. I think it was, they requested number 3 again. We'll do 2, 3, and 4 here. And yeah, we'll do the right side on this one too. Fall 19, test 3, part 4, when we get back. See you very soon.